Okay, welcome back. So it's already 11 o'clock, and we can now continue with our transform coding discussion. Now, the next thing that I will talk about after covering the discrete cosine transform, the first thing was the discrete Fourier transform, the essential transformation. After that, we have seen the discrete cosine transform, which was a real transform, and it's very much useful in compression purposes, particularly for images. I may want to mention about the discrete sine transform, which is not particularly useful, but it's worth mentioning now that we have the discrete cosine transform. There's also the discrete sine transform with a transform matrix rendered in the form of this matrix I and nth value is consisting of 2 over n plus 1. So it's like 2 over n, but since we are using plus 1 in the denominator of the period in the sinusoid, it's n plus 1 now. And it's notated or formulated as this. So if you don't consider the plus 1 terms here, like I plus 1, m plus 1, and n plus 1, it's like pi I m over n. So it has the same or similar structure as discrete cosine transform, where it is 2 pi I m over 2n. So 2n is the period. It's like folding again, but this time the DFT analogy is like you fold, but then fold again from the negative side, which makes it not symmetric but antisymmetric. And for antisymmetric sequences, this time the Fourier transform becomes purely imaginary, and this imaginary part will correspond to the sine transform. So it's related to the imaginary part, not the real part, but the imaginary part of the Fourier transform, discrete Fourier transform. The thing is that it's related, or it may be making sense for sequences, again, of the structure autoregressive 1, but this time as rho approaches to -1, not +1. So for high frequency, or if there is an inverse correlation, which is still a high correlation, by the way, but if one signal is one pixel value is a, and then the neighboring pixel will have the value of -a, for instance, such kind of a negatively high correlation, then the discrete sine transform will perform well. The reason that it uses +1s here is because when I and m, or either of them, may become 0, then if you don't use the +1s, it will be sine of 0, which is totally 0. So a column or a row will be completely equal to 0 in this discrete sine transform, which will reduce the rank of the matrix. Therefore, it will not be invertible. So the inverse sine transform will not exist if you don't use this +1s here. That's the necessary reason. And these signals, where for which the DST will become like KLT, will become optimal, these signals will never appear. I mean, in real life, for natural images, we don't have this kind of a negatively high correlation among samples. So it's not used, but there it is, mathematically, here it is, and we have to know about it, maybe. And then the next transformation is the Hadamard transform. This one and the one after this that we will see, which will be the Haar transform, they are not like smooth sinusoid shape basis transforms, but they are rectangular box shape basis transforms. Therefore, we don't have this cosine or sine or e to the j omega and things like that, which will produce smooth alterations of the frequency. These will have rectangular box shapes in the form of bases. And particularly this Hadamard transform is a very interesting and funny thing to construct. It is recursively constructed. The first Hadamard transform H1 it starts from the famous 2x2 transform that we have been talking about in the last few weeks. Because in 2x2 we don't have any other transform, right? So it also has the same. And starting from there, we have any nth Hadamard transform to be equal to 1 over square root of 2 times the previous Hadamard transforms here, with the sign of 1, 1, 1, and minus 1, like this. Notice that there is a minus here for this corner coefficient or corner segment. So starting from H1, you can find H2 using H1, or H3 using H2, etc. It just grows. And the size of the Hadamard transform is always 2 to the n by 2 to the n. Okay, that is the transformation. We don't have a 6 by 6 or 5 by 5 Hadamard transform. We have 2 by 2, 4 by 4, 8 by 8, 16 by 16, etc. And we may talk about, or I may give some examples of at least 2 by 2 and 3 by 3. The 2 by 2 Hadamard transform is using H1. And inside H1, I already have 1 over square root of 2. And now I will use another 1 over square root of 2 in each iteration step, which will make 1 over 2. And in this corner, I will have 1, 1, 1, minus 1. And here again, 1, 1, 1, minus 1. Here again, 1, 1, 1, minus 1. And in the last corner section, it will be negative of it. Minus 1, minus 1, minus 1, 1. So this is the 2 by 2 Hadamard transform. Now, if you look at the rows or the columns, they are the same. It's transpose symmetric in a way. You will notice that there are some oscillations, but the oscillations are not in the form of increasing and decreasing smoothly, but they are in the form of box shapes. The first, for example, shape is a straight line. And then we have +1, -1, +1, -1. And then we will have +1, +1, and -1, -1. So it's just one upgoing and one downgoing rectangular kind of shape, the box shapes. So we cannot really think of the frequency here, because the box shapes will have technically indefinitely many frequencies, high frequencies, but we can say that some of the frequency-like substance in these rows and columns are still increasing and decreasing. They have some kind of a frequency, but that frequency from now on for these rectangular shaped transforms will not be called frequency, but they will be called sequency, which has a similar meaning, by the way. And the sequency will be notated as the number of sign changes. What do we mean by that? For example, let's look at the first row here. How many sign changes do we have here? What's the number of sign changes? It's 0, nothing. So the sequency of the first row is 0. And we expect the sequency or frequency in an ordering within the rows or within the columns. When you shuffle one of them, the other one will be automatically shuffled. Now let's look at the second row. I can see that there is a sign change from plus to minus here, 1. Another one from -1 to +1 here, which is 2. And then another one from plus to minus 3. So there are 3 sign changes. As a matter of fact, that's the maximum number of sign changes that we have. So the sequence of this is 3. If you look at the next line, there is only 1 sign change, which makes the sequence 1. And for the last row, there are 2 sign changes. So the sequence is 2, which is some sort of bad, because for technical reasons, we want the sequence or frequency in the ascending order, from the first row to the last row, or from the first column to the last column. In that way, it will be more practical to make implementations of the coders and things like that. So these rows, which will automatically shuffle the columns, rows must be ordered. Like the first will be the 0, which is in the correct place, by the way. But then after that should better come this row, and then should come this row, and then should come this row, right? So that kind of a row shuffling is necessary, it seems. But we don't for the time being, because we will generate first. And let's see what's happening when we generate them. Like, let's see what is the third Hadamard transform, which is 8 by 8, by the way. And there will be further 1 over square root of 2 in the scaling, the total scaling. So there is, the scale is 1 over 2 square root of 2. And then it's easier to render. It will be starting with 1, 1, 1, 1, which is H2. I'm writing this H2, top H2 here. And 1, minus 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1, 1. And then I will repeat it. Sorry. 1, minus 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1, 1. This corner will be the same. 1, 1, 1, 1, 1, minus 1, 1, minus 1, 1, 1, minus 1, minus 1. It's a tedious thing, I know. 1, minus 1, minus 1, 1. And the last bottom right corner is just the negative of this 4 by 4 thing, which makes minus 1, minus 1, minus 1, minus 1, minus 1, 1, minus 1, 1, minus 1, minus 1, 1, 1, and minus 1, 1, 1, minus 1. Right. If you're working like a computer, then it becomes a tedious job, but it's not a big deal, as you see. This portion is just the negative of these other 4 portions. But let's take a look at the sequences. Let's calculate them. The first has no sign changes. The other one will have 7 sign changes. And then the third one will have 1, 2, 3 sign changes. The other one will have 1, 2, 3, 4 sign changes. The next one will have only 1 sign change. And then I will have 1, 2, 3, 4, 5, 6 sign changes. Then I will have 1, 2 sign changes, and then I will have 1, 2, 3, 4, 5 sign changes. So the sequence is again pretty much shuffled, and it must be corrected. Like this must be the second row. The first row must be kept there because it's the lowest sequence, and then should be this one. And then should be this one, then this, then this, then this, then this, and the last one must be this row. You have to make that kind of a shuffling. And when you make the correct shuffling, the transform will also be named a little bit differently. It will be the Walsh-Hadamard transform. You may believe it or not, or actually you must, because it's maybe an exam question of yours to discover the rule of correctly making the shuffling, because these shufflings are looking quite arbitrary, but they have some nice meanings in terms of their binary representations. For example, these will be 3-bit represented because the numbers are between 0 and 7. And if you write those in bitwise form, this will be 0, 0, 0, this will be 1, 1, 1, and this will be 0, 1, 1, etc. This will be 1, 0, 0. Okay, these binary representations. From these binary representations, I'm not going to tell you any further, but it's your duty to take a look at the literature to find a way to assign correct row ordering. And when you order them, shuffle them correctly in the rows, the columns will also be automatically shuffled into the correct format. Okay, so that will be your exam question. But even if you cannot do that, you can at least put a rule-based methodology to deliberately put some rows to their corresponding correct places. But it may become more and more difficult if it is, for example, 16 by 16, 32 by 32, etc. It will be very large. And then what is the idea? What's the logic in this sequence? What kind of a logic will make or generate these sequences is a good mathematical exercise. But it has nothing to do with compression, though. I mean, for compression purposes, of course, first you have to correct them, and then you have to apply them. And the application for these, for such Walsh-Hadamard, and then we will see Haar transforms, are that they are very easy to implement. Their implementations do not require any kind of multiplication. They require only addition and subtraction, because the coefficients are either 1 or -1. So you add this coefficient, subtract this coefficient, add this coefficient, subtract this coefficient, etc. You don't multiply really with something. And after the addition and subtraction, in the very last stage, you multiply everything with something, with a number. But for the others, for example, this discrete sine transform, you have to multiply everything, every item in your signal with this sine value. And this sine value is difficult to obtain. It's a real value, or you may have a table, lookup, but even afterwards, it requires multiplication. And multiplication is definitely way more complicated than making simple additions and subtractions. So it's very good to have coefficients of 1 and -1 in your transformation. If you have a poor computer, or if you have a very small digital electronics circuitry, this kind of a summation and subtraction will be enough for you to make the implementation, which is not as good as, of course, DCT, for example, discrete cosine transform, or other transformations, but it's still very good. I mean, it really improves the bitrate efficiency that we will be seeing probably next week. So it's better than many people may expect, although despite its simplicity in this format. And if you want to find H4, which is 16 by 16, then you have to use these 8 by 8 blocks here, 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 and the negative of it at the last final stage. That is the Hadamard and its corrected version, Walsh-Hadamard transform. Now, the next thing that I want to show you is the Haar transform. The Haar transform, again, will have this. I will show it by examples. I'm not going to describe a methodology for the construction of matrix transforms, transform matrices. Because of a reason, because essentially this Haar transform is not really implemented by multiplication with a matrix. It has a different implementation. So we will continue with that different implementation, and I will only mention about those things very briefly. The Haar transform in the smallest case, 2 by 2 case, is of course 1, 1, 1, -1, as usual. It's the only 2 by 2 transform that we have. But starting from H2, things start changing, and I will try to explain what is changing from these examples. First of all, it's again multiplied with an extra 1 over square root of 2, which makes it 1 over 2, just like the Hadamard transform. But this 4 by 4 transformation is a little bit different. The first row is all ones, but the next row is just splitting the left-hand side from the right-hand side. So it's a little bit different. This is an interesting matrix that we will have. We will try to act like we are trying to get some equations of these numbers, because this is a transformation. It will make a matrix, and we will multiply this matrix with a vector to obtain a vector. So here, the result vector is what I'm trying to construct here. The result vector's first item is consisting of the summation of the input vector numbers divided by 2. And then I will separate the left-hand side and the right-hand side. The left-hand sides will be positive, the right-hand sides will be negative. Subtract the second half from the first half. So the two numbers that I obtain will not be sufficient for me to resolve what individual values I have. For example, for x, y, z, t, and it will give me A, B, C, D, right? So using A and B, I won't be able to resolve X, Y, Z, and T. But I will have a coarse resolution of a combined version of X and Y and Z and T. If I say X plus Y is, for example, Q, and Z plus T is P, I can resolve Q from P with these formulations, because the first two will give me the summation of P and Q, and the last two will give me the subtraction, the difference between. Sorry, A will give me the summation of P and Q, and B will give me the difference between P and Q. Okay, so I can resolve P from Q. P is these two, Q is these two, for example, let's say. But it won't be sufficient for me to resolve X from Y. So I have to resolve X from Y. And how can I do that? I can put a +1 here and a -1 here and ignore Z and T. So this difference between X and Y will also help me to discover what is X and what is Y if I know P, for example. P is the summation, and this is the subtraction between these two. So from two unknowns with two equations, I can solve for X and Y. But how can I solve for Z and T? For that, I have to ignore X and Y and write it like this. 1 and -1 for Z and T, which will help me to isolate Z and T separately in the inverse transformation. But at the same time, it's doing some kind of a frequency or sequency concept as well. First of all, the sequency of this one, or the frequency of this one, is 0. It's okay. And the frequency of this one is, the sequency is 1, but the 1 is like 1, 1 and -1, -1. So it has 1 up and 1 down. In the next two rows, the situation becomes different. It's again a sequence of 1, but this time the boxes are half the size, like +1 and -1, and the others we don't have. So it's a squeezed version of a box shape, positive and negative box shape, which was longer previously in the upper row. Now I squeeze it to half. Therefore, its frequency is essentially higher. The frequency of this is higher than the frequency of this, because it's short. It's squeezed version of the other thing. Consider like a sinusoid. You have a sinusoid, sine wave, and if you squeeze the sine wave, the frequency increases. It's like that. This one has the same squeezed frequency, but its location is different. So these two have higher frequencies, but they have some localities. It's one of the high frequency is at the left-hand side, the other high frequency is at the right-hand side. So from A, B, C, and D, unlike the previous DCT or Hadamard transform and discrete Fourier transform, where when you look at the transformation output, you will not see the time data. When you look at these, actually you start seeing the time data. It contains some time information. What do I mean by that? For example, when you look at the value C, it's actually related to the x and y only. Here, the first two coefficients located there. It has nothing to do with Z and T, which are located here. So C shows me some information from the left-hand side of the data, and D shows me some information from the right-hand side of the data. So when you when you apply the hard transform, you start seeing the data in a sense. A high-pass version of it, by the way, not a low-pass version because it's +1, -1. It's a high-pass filter. So C contains some high-frequency information in a located manner, located at the left and located at the right. And those locations become more and more eminent if the transformation matrix becomes larger and larger. For instance, H3 is 1/2 square root of 2, of course, an extra square root of 2 comes into the picture. Yeah, I forgot to mention about what is happening at these points for normalization purposes. I forgot to normalize these rows. Although the idea of 1 and -1, 1 and -1 are correct, the norm of these vectors become unequal to each other. But they have to be equal. They have to be unit norm. For example, what's the norm of the first row? It is 1/2. There's a 1/2 here. So take the square of that, 1/4, plus 1/4, plus 1/4, plus 1/4, it makes 1. So it's unit norm, it's normalized. The norm of this one is also automatically 1, because if you take the squares, these -1s don't matter. But if the norm of this one is if the value is 1/2 and 1/3 here, and you take the squares of it, they become 1/4 plus 1/4 plus 0 plus 0. So it becomes 1/2. And the square root of 1/2 is 1/square root of 2. So the norm is not 1. The norm is 1/square root of 2. How can we normalize it? The way to normalize it is to change these to square root of 2. Then the norm will become 1. So it's not 1 and -1, it is square root of 2 and minus square root of 2. Same is here. Okay, we have to make this kind of a correction. It's like we will be increasing the resolution, the time resolution, and every time we increase the time resolution, we must make it shorter, and every time we make it shorter, we must further multiply by a further square root of 2. You will see what I mean with this example of H3, which starts from 1, 1, 1, 1, 1, 1, 1, 1, of course. And the next row will be, half of it will be positive and the other half will be negative. And then we will continue with further splitting this half into 2 and this half into 2 for reconstruction purposes. So it will be like, but I will erase it. So if you're writing, be careful about that. 1, 1, -1, -1. And the others will be zeros. And the next time I will split the second half into 2, 1, 1, -1, -1. But the problem again is about the norms of these rows. And in order to normalize, I have to again multiply by square root of 2. So essentially, let me erase these and let me write them in the correct way. Square root of 2, square root of 2, minus square root of 2, minus square root of 2 is what you really need to say in these two. But once you do that, you're not finished, because these two are still combined. These two are still combined, these two are still combined, and these two are still combined. So you have to separate them with even shorter boxes. And it's going to be like 1 minus 1, and all others are zeros. And 0, 0, 1 minus 1, all others are zeros, etc. There will be 4 of them, by the way. But again, the norms are even in deeper problem. The norm will be too little, so we have to normalize it to 1 by further multiplying again with another square root of 2. Previously, it was already multiplied by square root of 2. A further multiplication with square root of 2 will give you 2 minus 2, 2 and minus 2, 2 and minus 2, and 2 and minus 2. So the norms of these rows, and if you take a look at the columns also, they will be 1. All right, so this kind of a transformation, this transformation is from top to bottom increasing in frequency, but in some discrete steps. Like this has a frequency corresponding to, let's say, omega, and these two will have a frequency of twice of that, because they are squeezed by half, so the frequency increases by twice. And these 4 things are even squeezed further to half of it, so 4 omega is what we have here. And the first one is just 0 frequency. So the frequency is increasing in that kind of an order, but it stays the same for several rows. For example, for all these 4 rows, the frequencies are the same. Only the positions are different. It's in the form of a sliding manner. These 2 minus 2 is tracing my signal from top to bottom. So the last 4 elements of the after the transformation, after the transformation, you will have, this is an 8 by 8 transform. The input is size 8, so the output is also size 8. The last 4 of those 8 coefficients will have the same frequency content, but they will correspond to the first part, the middle part, and then afterwards, and then the last part. So local information will be available. So the output will contain frequency information like DCT, like DFT, like Hadamard, but it also contains some time information. But none of them are perfect. It contains only some frequency information. For example, this is a very short Fourier transform. Therefore, it's not really showing the frequency content, but it shows more or less the frequency at the location, and the location is also ambiguous. Around these 2 pixels, or around these 2 samples, the frequency is more or less something like this. Such transforms that produces both the frequency and the time information are called time frequency representations. And this hard transform is a first attempt to resolve in time and frequency, but in an imperfect way. The imperfect way is like this. There is time resolution at the local, at the horizontal direction, and then there is frequency in the vertical direction, let's say. The first one will have quite an ideal frequency resolution, which corresponds to the DC. Omega is equal to 0. The first row will give you that. Sorry. So the frequency resolution ambiguity is very low. In fact, it's 0. Okay, this is a very narrow rectangle. But the time resolution is completely gone. We don't know where this DC appears in your data. It appears everywhere. So there is no time resolution. And then one step up when you go, you again have the higher frequency. But this ambiguity is now starting to obey another rule that I will explain. And the frequency resolution is reduced. The frequency is 1 higher, but there is still no time resolution. We don't have any time resolution. Afterwards, since the filter size becomes half, the frequency resolution becomes half. And the ambiguity becomes double, but the time resolution starts to appear like this. So here, from here on, it starts showing, for example, this row multiplied the signal will give you information regarding only the first 4 samples. So there is time resolution. It will show you the first half of your signal. And then in the next row, it also shows you the second half this time. And when you go up one further level, the frequency resolution, I will have to erase some parts because it's like I'm making an inappropriate box here. It's more like this. The frequency ambiguity becomes twice of the previous, but the time, this frequency ambiguity is twice the ambiguity of this one, which is 4 times the ambiguity of this one. But the time resolution becomes better. It's twice better resolution. So this ambiguity is half the ambiguity of the previous, which is half the ambiguity of the previous, which is everything. So as you go upwards, it's like you start having more and more frequency ambiguity, but the time ambiguity becomes less. The thing is, these rectangles that you have the same area. Their width becomes half and the height becomes twice. The ambiguity rectangles I'm talking about, which is delta F times delta T. Delta F is the frequency ambiguity. Delta T is the time ambiguity. And from the Heisenberg's uncertainty principle, which is in the form of a Fourier transformation, this is always greater than or equal to 2 pi. And you cannot come smaller than this one. So you cannot really locate a signal and exactly determine the frequency of the same signal. You need to have a wider region of that to evaluate the frequency. And then because of that wider region, the location starts becoming ambiguous. So delta F times delta T cannot be both discovered at the same time. This is also known as the Heisenberg's uncertainty principle. because in physics, the same Fourier relation holds for the position and the momentum. And we know that delta P times delta x, sorry, it's not T, delta x is greater than or equal to something, Heisenberg constant or something like that. I really don't know that one. But I know that the relation is the same here. You cannot determine the momentum of a particle and the position of the particle with indefinite resolution. You are limited by this uncertainty. And this uncertainty has nothing to do with measurements. It is mathematical. You cannot avoid it. You cannot, it's not like, because of my poor measurement system, I'm unable to measure it. No, it's not like that. For the measurement, you have to have the data, and for measuring the data, you're losing the sharpness. So it's very much mathematical. This Hadamard transform is a first example of this time frequency representation obeying the Heisenberg's uncertainty principle. The others are also obeying the Heisenberg's uncertainty principle, but in a very extreme way. For example, if you apply this Hadamard transform that you see on the screen, then you will lose all the time information. Delta T will be the largest, and you will have the excellent frequency resolution. Okay, the highest frequency resolution, because everything is transformed into frequency. Same in DCT, same in DFT. So they totally transform into the frequency or sequency domain, whatever domain that is. They lose all the time information. There is no time information. You're looking at the Fourier transform, for example. T is not there. But using Hadamard transform, you are looking at some T within some ambiguity, but whenever you look better at T, you have less information regarding the time resolution. But the construction of this matrix is relatively difficult as compared to the Hadamard transform or the discrete cosine transform. And there is also another extension of this. There's a better way of implementing the Hadamard transform, and that better implementation is called subband decomposition. What do we mean by that? Subband decomposition is an interesting mathematical tool, and the relation between the subband decomposition in matrix transforms and subspaces in general that we have seen in the beginning of the transformations, the linear algebra basis things, in other words, they have very interesting relations, but I'm not going into the details of those equalities and relations, because they require literally a whole semester of lectures about subband decomposition. And they are related to so-called wavelets, which is a totally new topic. So since our topic is about compression and coding, all I will be saying is that this matrix implementation can be implemented using a subband decomposition, which is in a different format. And the format that I will show you will be this. And it's a streaming format, by the way. It's not really chopping into vectors and multiplying those vectors with matrices. I'm not chopping the vectors. As the data is coming, it's like in the form of x of n, the signal itself. The signal itself is flowing, and that flow is decomposed into branches, which will be like vectors x, y, z, t versus output vectors a, b, c, d. Now x, y, z, t is flowing, and the output of the decomposition will generate a here, b here, c here, d here, etc. So that kind of a decomposition will be happening. And it is done by the fundamental split is into two-channel band or two-band splitting. We have a filter here, H0, and another filter here, H1. And typically H0 is a low-pass filter. And for Hadamard sub-band decomposition, I will give you the filter coefficient. It's a two-tap, very small filter, by the way. And then a downsampling by a factor of 2. So these two outputs here will be like a transformation from the input x of n into x sub L of n and x sub h of n, or x0, x1. Some very different names could be given here. One thing that you have to understand here is the rate of the input and the rate, combined rate of the output branches. Suppose that the length of the input is finite, let's say 1000. What is the length of XL and what is the length of XH is the thing that you have to consider. And here, if the filters are short, you can ignore the convolution. The convolution with a relatively shorter filter, if the signal is long but the filter is short, you can say that the size of the size after filtering does not really change. So the length here is n, for example, capital N, and the size here is also capital N, more or less. And after downsampling, the length of this will be n over 2. And the same thing happens here. The length of XH will also be equal to n over 2. And when you combine these two, then n over 2 and n over 2 combined will give you length n. So it will not be inefficient in another way. Okay? In that sense, this transformation is not inefficient. It's like multiplying a vector with a square matrix and the output is the same length vector. By the way, this one will give you a 2 by 2 transformation. This thing corresponds to a 2 by 2 transformation. And here, H0 filter is 1 over square root of 2 plus 1 over square root of 2 Z inverse, which is, you can think of a two-tap filter of 1 over square root of 2 and 1 over square root of 2. I wrote it in the Z transform domain, so wrote it like a polynomial, but the coefficients are 1 over square root of 2 and 1 over square root of 2. That is the low-pass filter. And guess what? H1 is equal to 1 over square root of 2 minus 1 over square root of 2 Z inverse, which is another two-tap filter in this format. It's a high-pass filter, one positive, one negative. So when you apply these, you will decompose into the low-pass and high-pass branches. And it corresponds to a 2 by 2 Hadamard transform. But how about the 4 by 4 case? The 4 by 4 case works like this. I will draw it with a different color. Let's draw it with the blue color. This XL of n, the low pass, will be further decomposed into two further branches. So what are the rates now? The rate here was n over 2, and here the rate will be n over 4, and this will also be n over 4. So what is the output? How can you render the output? The output can be rendered as n over 4 from here plus n over 4 from here plus n over 2 from here, this one. And the summation will be again n. And this is a 4 by 4 Hadamard transformation. By the way, this H0 here is the same H0 as this one. And this H1 here is the same H1. They are the same filters. I'm using those filters repeatedly, again and again. Now, if I further try to decompose, I will do it again in the low pass branch. Like this. And these will be the outputs. So let's look at the sizes. This one was n over 4, so this is n over 8. This is n over 8, n over 8, n over 4, and n over 2. If you add these 1, 2, 3, and 4 chunks of signals all together, they will give you n. So the rate does not change as you split further. But the transformation, hard transform in the end, will be like this. You will have, let me continue with the green. It will be A is here, B is here, then C is here, and finally, this is, let's say, equal to D. D is here. So the output after the transformation in the form of a matrix, if you're thinking in the form of a matrix, will essentially look like this. Some short A's. Let's say the input is length 8, so the output of A will be 1. Why is it 1? Because if the input is periodic with 8, okay, downsampling by 2, and then filtering and downsampling by another 2, and then filtering and then downsampling by another 2 means downsampling effectively by a factor of 8. If you 3 times downsample by 2, it means you downsample by 8. And the input is periodic with 8. You do some filtering, but it doesn't affect the period. The period will still be 8. So when you downsample effectively by 8, this A will be a constant thing if the input is periodic with 8. This B will also be constant. However, this C will not be constant. It will be a periodic with 2. There will be 2 numbers of C. It will be C1 and C2. Okay. This one, if the input is periodic with 8, this D will be periodic with 4. It will have only 4 samples, D1, D2, D3, and D4. And then again D1, D2, D3, and D4. And then again D1, D2, D3, and D4, etc. So I'm going to write them that way. Then I will have A, B, C1, C2. It's not long enough, unfortunately, so I will erase it. And then D1, D2, D3, and D4. So this will be the output vector if the input is periodic with 8, if x of n is periodic with 8. If you say that those 8 periodic input samples are x1, x2, x3, x4, x5, x6, x7, and x8. And then if you apply it, if you apply that input to this matrix, okay, then let's say that is H3 matrix, then you will obtain this output. So H3 times X will give you this. A, B, C1, C2, D1, D2, D3, D4. Why did I say A and B separately and then there are 2 C1 and C2s? Because it's here. A is obtained by the first row and B is obtained by the second row with the multiplication with the input vector x1 to x8 here. And then C1 is obtained by multiplying it with this row vector, and C2 is obtained by this. So C1 will show the left-hand part, left side of the signal. C2 will show the right side of the signal. And then I will have D1, D2, D3, and D4 with the multiplication with the input, multiplication with the input. It will generate those outputs. So D1 will show you the first 2 items, and D2 will show you the second 2 items, etc. And it is obtained by a 3-level so-called subband decomposition. Now, the final thing that I want to tell you here before stopping completely is the following. Or maybe I shouldn't say that because it may be left to next week, I guess, because I want to show why these can be reconstructed, and the reconstruction of this from ABCD data back to X input data, which is in the original form obtained by the inverse multiplication with the inverse of the matrix. It's not necessary. There is a subband reconstruction corresponding to this subband decomposition. we have to talk about that a little bit. And furthermore, these H0 and H1s for the Haar, they are given like this, but there are other subband decomposition filters which are very much appropriate, known as wavelets. There are other wavelets too. And Haar wavelet is the shortest wavelet that you can have. And it's not the best wavelet, by the way, although it's good enough. There are better performing wavelets. So if you use different H0 and H1, which will require different reconstruction filters, okay, we didn't mention about them yet. So we jump into a very fascinating and interesting area of a transformation. It's a new way of doing the transformation. It's called wavelet transform or subband decomposition. And it's very good for compression purposes too, because of the energy difference between A, B, C, and D. If you want to reduce the energy of D, for example, you can get rid of them completely, which will be giving you a lot of compression ratio. You can totally get rid of these if their energies are small. And these are, by the way, orthonormal transforms. So if you get rid of the item in the transform domain, the amount of error that you make after the reconstruction will be the amount of data that you chop off. And if its energy is small, it means you're doing very small distortion. The error is also very small then. So we want to make this thing small, this thing small, and this thing small. How can we design these filters in such a way that one of the branches really will be reduced? We will talk about those things. We will see how can we assign bits to these A, B, C, and D items. And the bit assignments will be the same for wavelets, like these subband decompositions, as well as other transformations like DCT and things like that. They're also valid for matrix transformations too. But this is not a matrix transform, as you see. It's a different, quite a different way of taking the transform. And it's easy because it's just filtering and downsampling. It's as easy as making a matrix multiplication. And in fact, this one is a little bit more efficient than that. So we will talk about these things in the next week. So right now I will stop at this point and we will continue next week. Next week, therefore, we will again have some classes, but I'm not sure about the week after that. So next week, we will be also talking about how you will be making the presentations of your projects. So think about those projects. You should start thinking about them. The projects will be presented in the final weeks. We will make a decision for that, and we will allocate time using Doodle voting, and you will choose your time slot for those presentations. I'm not taking questions regarding these projects for the time being, but next week, please, if you have any questions, please come up with those questions and you will have to ask them, okay? So right now, I'm ending the recording and the meeting. But if you have any questions regarding this topic, the course, then of course you can ask. So I will give you a few seconds if you have any questions. If not, then I'm ending the meeting and let's meet again next week on Monday. Okay, see you then. Goodbye.
See you.